For me, this is very important video, not only because the PPA is the strongest filament type I ever tested, but I'm very curious about its core version, and I can compare it not only with the regular carbon fiber version, but also with pure base material. Hello, welcome back. About Siraya Tech, I already tested the resin materials, but recently they started manufacturing filaments too, and their PPA-CF has one of the best strength to price ratio. And now we have here PAHT, high temperature polyamide or nylon, based on PPA or polyfilamide. PPA has better thermal and chemical resistance compared to regular nylons like PA6 or PA12. And it's Siraya and not Syria, dear YouTube auto dubbing. Earlier on this channel I already tested PPA-CF from different brand, and it was the strongest filament I tested so far, but it is also very expensive. But here we have quite affordable prices, and if we have a similar mechanical properties, this would be great. And I'm very curious about the core version, because here we have three types. Let's go step by step. PAHT, without carbon fiber, superior material properties, super abrasive resistance, low friction and self-lubricating, ideal for gears, bearings and components under constant wear. I already tested earlier a wearing of the filaments, and the nylon and TPU are two more wear-resistant filament types. Only with the TPU we have more friction compared to the nylon, so for example it is good for shoe bottoms. But if you need a lower friction, then nylon is better. And here it looks like it is even superior in this case. It has great moisture resistance. The sensitivity is 1/5 compared to the PS6 according to the website. And on one place it has annealable filament, but the other place it has that annealing is not recommended with the regular version because it can warp. PAHT-CF reinforced with carbon fibers is the next type. It has 15% shop carbon fibers. And it is stiffer, more rigid, easier for printing because we have less warping and shrinking, and theoretically it is more temperature resistant too. And something really new, and I didn't test anything similar on this channel, PPA-CF Core. It has 25% carbon fibers concentrated in the center of the filament, and according to the website, this will reduce the nozzle wear, reduces fiber exposure, for those with arms full of wounds which don't heal, whatever that means, and improves layer adhesion. I am extremely curious about this last property too. How is this possible? Well, the flow is laminar, this means it will not be mixed, and great evidence for this are those dual color filaments, because we have one color on one side and the other color on the other side, and when we print that object, it will have two different colors on two opposite sides, they will not mix. So something similar we should have here, that core of carbon fibers will stay in the center of the printed line. Let me explain it on this animation. So we have our core filament. As you can see, the core is not touching the nozzle, and if we print with it, it should stay in the center of the line. And if we print with the next line, we can see that the nylon is touching the nylon. We don't have the reduction of the contact surface like with the randomly placed shop carbon fibers. And additionally, fibers are not exposed, which is maybe better for our hands. But to be honest, I wouldn't worry about this too much. About print settings, we need a 0.4mm nozzle or bigger, and of course because of the carbon fibers we need a hardened steel nozzle or some similar hard material, and of course we need an enclosure too. About bed temperature, 80 degrees Celsius in all three cases, PEI with some glue stick on it and it will be fine. For non-carbon fiber version, the nozzle temperature between 260 and 280 degrees Celsius. For two carbon fiber versions, the nozzle temperature between 300 and 320 degrees Celsius. And I want to do this printing on X1 carbon, so the maximal temperature here is 300 degrees Celsius, which will be my settings. Print speed up to 120 millimeters per second, and I calculated it is approximately 10 cubic millimeters per second flow rate. Cooling fan speed between 20 and 60% for the regular version, and for the carbon fiber version it can be switched off. About annealing, the temperature between 80 and 100 degrees Celsius and the time between 4 and 8 hours, and at the end slow cooling. For PAHT regular version without carbon fibers, it says annealing is not recommended because the object may warp. Now actually here I have to make a decision if I want to anneal them or not, but actually I'm always curious about the mechanical properties without annealing. Of course, few test objects are annealed, for example for the temperature test, layer adhesion and a few others, but most of the test objects will not be annealed. But the annealing will be with some carbon fiber versions only, not with the regular one. Maybe just I want to see the warping or something like that. I'm starting with PAHT, and since I have different informations, I will start with temperature tower from 300 down to 270 degrees Celsius. Already mentioned that I really like their spools with a lot of information on them, only I'm missing the weight of the empty spool. This filament shouldn't be brittle. That's right. On the spool also information, the temperature between 280 and 300 degrees Celsius. It will get 2 hours of drying on 70 degrees Celsius and the printing will be from the filament dryer. Engineering plate with some glue on it. The start is okay, it sticks good to this engineering plate. And this is the last element on 270 degrees Celsius. Bed adhesion check. It's good. Looks nice almost on any element. A little bit more stringing I can see here on the higher temperatures. And also I can see a little bit more melted seams line here on the overhangs on the higher temperature. So I print everything on 290 degrees Celsius. The base is generic PA profile. I modify nozzle temperature to 90 degrees Celsius, sphere will be the flow rate, and the part cooling between 30 and 50%. Last few vertically printed objects. Looks okay so far. I will need few test objects for the annealing too. And since the layer adhesion is important here, I will have some additional test objects with 2 watts and 20% infill. From this second group, most of the test objects will be annealed. Wow, this work is getting bigger and bigger, so this will be the reference material and this group will be annealed. And same with the other two materials. And now PPA-CF, and it is almost in some kind of gray color. And only thing I notice here that there is no desiccant. I check in the bag and also inside the spool. I think it should be added. And usually with brittle filaments, companies use some kind of stick tape to lock the end of the filament. Let's see how brittle is this one. Very brittle. Now I don't need a temperature tower because everything will be printed on 300 degrees Celsius. Generic PPA-CF profile, 300 degrees Celsius, 8 is the flow, and I reduce the part cooling between 10 and 20%. Printing with carbon fiber version is even easier. The second group with some parts which will be annealed too. And now the core version, both are a little bit grayish color, but for the filling this one is much smoother compared to the regular carbon fiber version. Let's see how brittle is this filament. It is still brittle. And I noticed that this is definitely much harder for the cutting. I hope not too hard for this cutter here inside the extruder. I think I will have again limitation problem on the shear test. And of course great printing with this core version too. And the last group is printed too, the core version. And they look perfect. I'm very curious about the layer adhesion. Ouch. That was a hard cutting. Let's check what can we see under the microscope, and first I will start with the filaments and then with the printed objects. So these are filaments, and PPA we can see that it is smooth outside and inside. In the middle CF carbon fiber version, and we can see even on the edge those fibers. And the core version, it looks like it works because outside it is smooth and somewhere here inside we can see those carbon fibers. And these are printed objects, and the PPA looks shinier. I cannot really see exposed fibers on a PPA-CF, but if you place it next to the core version, it's obvious that the core looks more smoother and shinier. Now maybe on this one test object from the PPA I can see or it needs more part cooling or I have to reduce the temperature, and for the reference next to it is the core version. This is Sanlu E2 filament dryer. And I already know if I need 100 degrees Celsius inside, I have to set the temperature to 90 degrees. The timer expired, and another bug in this prototype machine that it don't turns off. I have to do it myself. I will wait until it cools down, only then I will open it. And now let's check the result. It cooled down together with machine. At the first look, this looks straight and this is quite deformed. Yes, so this is why they don't recommend annealing of the regular PPA. Let's check the shrinking. These are annealed versions, and I already mentioned that the PPA after annealing had some warping, but I believe that it is measurable. The design length is 80 millimeters, and I'm measuring above the elephant foot. 79.98, 80.07, 80.08, and now annealed versions. 79.68, 79.95, very minimal shrinking. 79.98, basically almost no shrinking. Off camera I will measure these annealed test objects in X, Y and Z direction, but don't forget, keep in mind that PPA will deform during this annealing process, especially you can see on these kind of objects. I just finished the measuring, this is the result. The design length is 30 millimeters in X, Y and Z direction, and now on the screen you can see everything recalculated in the percentage. Basically two carbon fiber filaments, very accurate. The regular PPA have shrinking in X and Y direction and some expansion in Z direction. The tensile test with horizontally printed test objects, this is PPA, and even this material is quite strong here. And now the carbon fiber version, one of the strongest I ever tested. And now the core, I hope it will be similar, and it is even stronger, and my expression. So as I mentioned, even PPA is quite good in this test, but two carbon fiber versions extremely strong. And now layer adhesion test, vertically printed test objects. I'm starting with PPA. These are those 4x4 mm solid inside. Carbon fiber version noticeably stronger. And the core, this should be stronger, and it is, but the difference is not so big. And now the annealed version, PPA, carbon fiber version, again much stronger, and the core even stronger. Now question is, why is PPA weaker here? There may be two reasons. One is the lower print temperature, and the other is not enough part cooling and you don't have nice aligning shape. Another layer adhesion test, a 10 by 10 mm smallest cross section area with 2 walls and 20% infill. PPA 63.8. Let's see the carbon fiber version. Slightly stronger. And the core much stronger, interesting. And these are annealed test objects, starting with PPA. This time very good. Carbon fiber version, still very good. And the core, extremely strong. The first conclusion here that annealing didn't significantly change the layer adhesion. Well, one exception I have here with the PPA, from some reason here it was better. Now why is the regular PPA weaker compared to the carbon fiber versions? I'm not really sure, maybe because it was printed on lower temperature, or maybe the part cooling is not enough and it was deformed and don't have nice aligning surface. Now the core version was stronger compared to the regular carbon fiber versions in both cases, but here where we have these two walls and hollow inside, it was significantly stronger, huge difference I can see here. And now the shear test, and I'm starting with vertically printed test objects. And in this case the layer adhesion is very important, and no surprises here, the core version was the strongest. And now switching to the chain hoist and this crane scale, because I know that here I'm expecting much bigger loads. With this equipment I can measure up to 500 kilograms, only this scale don't show the peak of one measuring, so I have to analyze the footage digitally, and here I have the freeze frame. With horizontally printed test objects, those carbon fibers really helps, and this we can see in the numbers. No big difference between two carbon fiber versions. With vertically printed objects, the layer adhesion is very important, and here of course the core version was the best. The hook test side by side all three materials. There is some difference, but not big. And this is the annealed version. And again we can see some difference, but nothing significant. And we can see this on the graph too. Creep test, the deformation under the constant load of 1.25 kilograms. $14.81, 12.23, 12.32, From these three, two carbon fiber versions are really good in these very stiff materials and they form very minimally compared to PPA. This is the last fifth day and only on the PPA I can see some deformation. On the other two carbon fiber version, basically this creeping is near zero. 1636, 12.27, 12.36. Removing of the load. The deformation on two carbon fiber version is equal, a little bit more permanent deformation on the PPA. On this graph we can see the distance between two reference surfaces, and on the carbon fiber versions almost no deformation. On PPA we can see some initial deformation and some creeping, but the creeping is the difference between 2 days, and that's what we can see on this graph. And the carbon fiber versions basically don't have any additional deformation. On the PPA we can see some creeping even on the 4th day. Compared to these materials it was weaker, but compared to some other average materials this is still very strong. Temperature testing though, whenever I want to record the temperature of the first deformation, but I'm afraid that I will have a small problem here. I think I will reach the maximum temperature of my equipment and most of these test objects will not even start to deform. These one test objects from PPA have this deformation, but it is from the annealing. This is speed up time-lapse video, and I thought nothing will happen until near 200 degrees Celsius, but the PPA started to deform quite early, at approximately 87 degrees Celsius. After this it slowed down, but later it continued with deformation. And then I have here jump in the time. And the next one was the PPA annealed version, which started to deform at approximately 199 degrees Celsius. And after this I stopped the experiment on 220 degrees to see how hard are the rest carbon fiber filaments. And they are still perfectly hard. The torque or twist test with horizontally and vertically printed test objects, and here I don't have annealed versions. Horizontal test objects, PPA broke quite early. 0.7. Wow. 2.47. 2.4.7. Vertical test objects with the same dimensions. 1.8, 2.4, 2.9. I saw this so many times. Vertically printed test objects have the same dimension, but the break load is bigger than the horizontal version, only it breaks more suddenly. 3-point bending test, distance between supports is 50 mm, and these loads will be placed one by one, and I'm measuring the deformation after 1, 30 and 60 seconds. Currently you can see the deformation under 2.5 kg, under 5 kg, and this is under 10 kg, and basically almost no additional deformation on carbon fiber versions. The deformation on two carbon fiber version is very similar, slightly less on the core version. Now the PPA it have a more deformation, but the additional deformation during the time is very minimal, so it really handles good this bigger load too. Another 3-point bending test, and here I have regular and annealed versions, and this is a little bit different because this follows better that ISO 180 standard with the bigger distance and with this radius. And I will just place 5 kg load and I will follow the deformation after exactly 30 seconds. Non-annealed versions, I am placing the load. And this is after 30 seconds. PPA annealed, which already have some deformation. And again placing the load, initial deformation. And after exactly 30 seconds. Carbon fibers really helps here, but effect of the annealing is not significant. Impact test with this half kilogram hammer, PPA, CF, Core, annealed versions, PPA which already has some deformation, CF annealed, Core annealed. Zero position one more time. Let's analyze the footage. This is the zero position after breaking PPA, PPA-CF, Core version, and this is annealed PPA, annealed PPA-CF, and annealed Core version. We heard that the base material is more brittle compared to the carbon fiber versions, and again effect of the annealing is not significant. And our results one more time without any additional comments. And these 3 lines will be added to that summary table for my Patreon supporters, so they can easily compare this data to any of those which I did in earlier videos. Basically, this is the only gift for my Patreon supporters. Sometimes they get early access to some videos, and I try to figure out some other motivation method. But anyway, huge thanks to all of them because they keep this channel alive. Quick conclusions for the end. PPA is a great material with fantastic mechanical properties. I don't really like the non-reinforced versions. The printability is not so good, and probably I should even lower the print temperature or increase the part cooling, but in that case, for example, the layer adhesion would be weaker too. These two carbon fiber reinforced have a great mechanical properties. I really like these materials. And the question if the core works, yes, we will have less wearing of the nozzle, the fibers are not exposed on the surface, and also we will improve the layer adhesion. And this can be seen not only in the layer adhesion test, but also on the shear and the twist test where I have those vertically printed test objects. About annealing. I don't really see the reason for annealing of the carbon fiber versions. The difference is extremely minimal. I could see a reason for annealing of the regular PPA because we could improve the temperature resistance, but unfortunately you saw that it will warp during this process. So in my case, in my future projects, I will not anneal these materials. Now I got several questions if those CHT nozzle will work with the core version 2. Yes, because I know that, for example, those dual core filaments will also work with those CHT nozzles. Only one property we don't have here, that's less wearing of the nozzle, because the center of that CHT nozzle will be exactly in the core of that filament. This was huge work, much bigger than I planned at the beginning. And a small reminder, don't forget to subscribe and click that notification bell button too if you like this kind of videos, because from some reasons my videos are not really recommended. Yes, my main motivations are my Patreon supporters and big thanks to them, and it's independent from the number of the views. But I'm always sad if this kind of big work will stack on, I don't know, 5 or 6,000 views. Anyway, if you have some other experience with these materials, write me a few lines down in the comment section. Thank you for watching and happy printing!